Session chairs. Marco's your first session chair. Find him, and then you can find the other ones later.
Yeah, and look on the website if you don't know who your session chair is.
Yeah.
Try the equipment beforehand?
Sure. Talk to your chair. Those are interesting things.
All right. Hi, I'm Tyler McMullen. He already gave me an introduction, so I will skip a bunch of that. But I figured that one thing I should probably do if I'm going to stand up here and talk to a bunch of like very educated, very like intelligent people like yourselves, I should probably give some of my qualifications so you know why I should even be allowed to talk here. So, what college did I go to? I went to none. I have 0 papers published currently. I have been working on compilers for a whole 3 years though, so lots of things to say about this. I've worked on 1 compiler. On the upside though, I have been working in industry for 19 years now, and I've been a CTO for the last 9 of those, right? So maybe I have something of value to say, maybe, right? So coming into this yesterday, I got here yesterday evening. Actually, the only person I knew here was Dion. So last night I went out with everybody and I got like a little bit of an education about what Prisk is about. So I had a few takeaways from last night that I felt like I should share first. I hope that like people will tell me if this is accurate or not. So the first thing I learned was, first thing I listened to was 2 people arguing about the definition of what it means to be robust. And my conclusion is that there is no conclusion. I still have no idea what robustness means. Beyond that, I enjoyed a conversation about different types of sandboxing. My conclusion was that no one agrees about what sandboxing means. I still don't know what sandboxing is, but I'm going to use the word repeatedly in this talk. So, finally, I listened to a spirited debate about the virtues of LaTeX versus Keynote. My conclusion to this one was to not rewrite my slides in Keynote, or I'm sorry, not rewrite my slides in LaTeX and continue to use them in Keynote because it has animations and color. So, I want to give some context to before I start talking about Lucet, it's useful to understand the types of problems that we're trying to solve and why we're trying to solve them at Fastly. So Fastly was founded in 2011. By all accounts, people would have initially looked at it and said, this is a content delivery network. If you're not familiar with what a content delivery network is, it's a pretty boring concept, honestly, initially. Essentially, it's, we have a whole bunch of servers spread all around the world, and the whole concept is, if you want to go to, say, for instance, the NewYorkTimes.com, you're not actually going to the NewYorkTimes.com servers, you're going to my servers, because they happen to be co-located, really close to you. Okay, so if you're in Australia, you're going to go to the one, say, in Sydney or Perth or Melbourne or wherever. You're not going to be going all the way back across the world to the US, right? And so those have existed for a while, since 1998. We came along in 2011 and started trying to do something a little bit differently with it, trying to add logic, a bit more logic into what the CDN could do. So we did that initially using kind of our own DSL based on an open source one called VCL. It is essentially programming the state machine in a request response flow of sorts, right? It is an extremely limited DSL. There are no loops, for instance. There is certainly no really anything. So a few years ago, we started trying to do something a little bit differently with this, which I will go into. But right. So kind of the way I'm hoping to go with this talk is give you a little bit of context to motivate the problems that we and others are facing with regards to especially edge computing, essentially, is what this is ultimately going to come down to. Then talk about how we've attempted to solve some of those problems, and then kind of talk about the problems that we are still struggling with or have just straight up given up on. Okay. So the way our architecture actually ends up working is it's actually really straightforward. It's we up there anywhere from 8 to 64 servers. We have some number of them. I don't have the number specifically in front of me, and I can get in trouble if I just start saying numbers live now, since we are now a public company. So there's a whole bunch of them. We have a lot of servers. We have a lot of POPs, right? But essentially what they are is just a bunch of servers and a set of switches that sit in front of them. The servers actually do the vast majority of the work. There's no routers. There's no control plane things built into these are like very stripped down data centers, essentially. So POPs are distributed around the world, like I said, and then we attempt to route traffic based on DNS and BGP shenanigans, essentially. The goal is to route users to what is like the closest POP. And what it means to be closest on the internet is kind of like a challenging thing to like stably define. Essentially, but essentially we're trying to go for like the lowest latency, even if it's not geographically the closest place. So, yeah. So in this case, they might go to that POP. So, what is more interesting, of course, is that in addition to like the internet changing underneath us, there's also obviously like the inevitable issue of like failures in the system, right? So, with thousands of servers, some of them are going to be failed at like all times. So even more than latency, we're actually built for resiliency. So in this case, if that POP were to fail, we would want to immediately be able to, like, for the very next request from that user, for instance, we want to be able to fail them over to like a different POP. So this implies something interesting about our architecture, I think. What this implies is that any node in the entire system, thousands of servers, and like billions of users, any node needs to be able to process any request at any time, right? Which when I like initially started working on this, I was like, oh, well, that seems like an obvious and easy thing to do, and now I'm like, oh, fuck, like this is a lot harder than what there are interesting problems that come along with this, right? So, so about what it means to process something in this context. So what I'm, like, the common way that people think about this now, and I hate this term, but it's like functions as a service, right? So you think about like Amazon Lambda or Cloud Functions or whatever else, right? It's like FAAS. I hate that, but like whatever. Like the idea here is that like our customer can bring their own program, which we have no faith in. Like that thing is entirely untrusted. Could be written in a variety of different languages. They can hand it to us and have us run it in reaction to any HTTP request coming into the system, right? Essentially around the world, any time of the day or night, right? So, like Lambda again is like probably the most common one that people think of. And this is like kind of an increasingly common element of like major company stacks, right? Part of my job as like CTO is like I end up going around and talking to a lot of our customers. We have a lot of customers spread around the world, and so I end up going in and chatting with them about like what it is that they're trying to do. And pretty frequently they're like, we have this data center here, it's kind of our legacy data center, and then we're moving this piece out to the cloud and this piece out to the cloud, and then we're using functions as a service for this whole thing, and like, okay, well, how do I fit this into my architecture, right? So most commonly, like these are kind of at the moment used in like a more or less centralized way. There's kind of an assumption that there's just one of them, or a small set of them in like a small set of locations. But increasingly, like the obvious direction that we're going in is pushing more and more of these out to the edge, like as close to the users as we can. Right? There are difficulties with that though, and so that's kind of where this whole thing is going. So in an ideal world, what we would do is, a user would come along. Hello, happy little user. User would send a request. We would figure out where that request was supposed to be destined for, what program we're supposed to be running in reaction to this. We would pop open a like Python or JavaScript or Ruby or whatever interpreter or VM in response to this. They would, let's say, they would impose some sort of state on it, right? They would sully this sandbox in some way. So essentially, they do whatever they want inside that sandbox, and then, like, ideally, we would be able to just throw it away, right? And there would be nothing else wrapping this. It would just be a bunch of VMs sitting in like a single process and whatever. Like, we're trying to like be efficient with our use of resources here. But obviously, like, that would be horrifically unsafe at the moment, right? This is not actually like what language runtimes, language VMs, and interpreters were actually meant for a lot of the time. Essentially, they assume security boundaries at another level, at like a layer above them. Looking like in the real world at the moment, that's where it gets ugly. So common practice ends up looking like this. Like a user comes along, again, we have our happy little user. They show up, they send their request, and then we go for this. So pop it in the sandbox. But before we can set the sandbox, we need something to run the sandbox inside of. So we're actually going to put like a container around this entire thing, right? And probably in addition to that, like maybe we don't have a container sitting around ready to go. We may also not have like a VM of some kind sitting around ready to go, right? And so this is where cold start time comes from. If you've heard anybody who uses Lambda or like anything else, or like, I should stop calling out Lambda, they're like perfectly fine. But like functions as a service platforms of some kind, you've heard people probably talk about cold start time and what a pain in the ass it is, right? And so that ends up coming from this stack that's having to like get spun up in reaction because it was not there when it was like when the request showed up. And we can see where that comes from. Like the sandbox in this case might take a millisecond or 2 or 10 to start up, and that's not a big deal, right? But then you start like considering the time it takes to start up a container, and the time it might take to start up a virtual machine, and you can kind of see how it adds up and how this starts to happen. And this all comes down to like safety, right? Like no one actually wants to have all of this crap around here. It's just that like we know that we can't actually trust language runtimes and language VMs. So, question? Can you wait for a little bit?
Yeah, we can.
Yeah. I'm gonna have like question slides in a couple places. Right. And so, because of this, because we have this cold start time, because we have to spin up this entire stack in reaction to like the user starting, we don't want to throw that stack away after we're done, right? And so that first user comes along and they add state to the system in some way. But again, we're not going to throw it away. And so like the next user comes along and they add their state, and the next user, and the next user, and the next user. And at the end of it, you have like this sandbox filled with states, right? And that state could be really anything. It's really down to like the person who wrote the program. The point is that the memory space of the program is not being thrown away after each request, right? And so that's all, like in the vast majority of cases, that's fine. Like the program is written fine, or like, the state that's associated with it is just shit. But the problem really comes in when something of value happens to. And so the interesting thing about this is that like this entire architecture that the vast majority of like functions as a service platforms are built on is designed to protect the infrastructure of the company that's running it, not the users from each other, right? To me, that doesn't seem problematic, right? I would much prefer to be able to go back to the model or go to the model where we have a single sandbox per user. So not only am I protecting my own infrastructure, but I'm actually being able to protect the users of the companies who are paying me to run their code, right? So, questions about the context, because I'm going to assume that all of you understand the context now.
So are you also concerned about function chaining, functions coming from different vendors and trying to isolate those from each other, or is it only about user isolation?
Are we concerned about being able to?
Sorry.
So I don't fully understand the question. So your point was being able to, do we care about being able to isolate the functions from different vendors from each other? So are you assuming that like a user comes in and they have like, their request might need to like hop between multiple different functions? Is
Yes.
that the?
Yes.
So yes, we are absolutely concerned with that problem as well.
Okay.
Yeah, absolutely.
I'm not at all familiar with this function as a service. Where's the data? I guess all this application needs to use persistent data somewhere.
Yeah, so typically there is an API of some kind to access various different databases, or be able to send requests out and get responses back from wherever. The problem, of course, is that like because that thing tends to be persistent, it's a common error to assume that it's going to continue to be persistent, and so you will frequently see things where like users or our customers will build applications on top of functions as service platforms, and then like it just occasionally breaks because it went away and it had to be restarted. So yeah.
But I guess maybe more generally, as a content delivery network.
Yeah.
Are you also duplicating the customer's data?
Yeah,
Or-
so
And then how do you ensure consistency and when you have all this
Yeah.
distributed stuff?
So our model is a little bit easier than that because we assume that there is an origin that the customer has that is persistent and durable and so on. We have effectively like a key value store of some kind but it's mostly a cache, right? Like they are well aware of the fact that it can go away at any moment, right? Because essentially we're supposed to, in many ways, just be an optimization on top of the existing stuff.
So how sparse are you assuming the requests are in time? Because that really affects the cold start problem, right? If you can keep the VM or the container warm for a very long time, then it doesn't really, there's no cold start issue. So what's the assumption on the...
Yeah, that's entirely fair. I don't necessarily have an assumption about that. There are some cases where like this works really well, and then you have like some lesser used applications, or really the problem is that like no one actually wants to build their entire application into a single one of these. They have like a whole bunch of them, and so there might be one that is hot all the time, and then you have 50 that are like cold the vast majority of the time. So I guess it really like comes down to the distribution.
And how predictable is the, let's say, the call graph between these functions?
So that one I actually don't see much of yet. Like that's one I hope that we will start to see more of, because I think it's like actually a really interesting use case, but like it's not all that common for you to see functions calling other functions in this way, at least in like a separate sandbox.
Okay.
Yeah, but I think like based on some of the stuff in like we're going to talk about WebAssembly next, but like based on some of the stuff the WebAssembly community is working on right now, I think hopefully we'll see that become a more common thing, right? I think it's especially useful like in a case like us where we have the customer who is providing their code, but we also may have like vendors, right? You know, maybe you have like standardization or like security standardization of some kind where you go like, okay, like I have my program which is going to call out to this other program which might call out to a third program. I don't necessarily want any of those things to have access to the full set of data that my program has, right? And so, yeah. Okay. Anything else? Great. Okay, so 3 years ago, we started working on this problem, trying to figure out a way that we would not have to go, okay, let's spin up this entire like god-awful container stack in order to be able to run our users' code. It was actually like kind of a circuitous path to get here. I actually started this project 3 years ago and spent a like truly embarrassing amount of time trying to get native client to work for this, embedding native client inside of a process. I ran into several problems with that. A, it didn't work for this particular use case. B, I didn't really understand the implications of needing, 84 gigabytes of virtual memory space per process. And the limits of, 48-bit memory space. And third, I had like spent so much time on it, and then it also got EOL'd by Google. So WebAssembly came along, and 3 years ago it was actually still pretty mature. So there's a lot of interesting things about WebAssembly, which I'm probably not going to cover in this talk. But there's like a lot of really great safety implications built into the specification itself. And as long as we can maintain those safety implications, we can provide some level of like security for our users, right? So the project we started working on was Lucent, which has gotten some traction. We recently moved it from just being a Fastly project to being part of the Bytecode Alliance, which is a thing that we founded along with Mozilla, Intel, and Red Hat a few months ago. So CraneLift is also part of that, as well as like the WebAssembly micro runtime and a bunch of other pieces as well. So we had a few different goals when we started this project. There are two primary ones though. One, like remembering that we're going to spin these up in response to user HTTP requests coming into the system really, really frequently. We do millions of requests per second across our network. We wanted to minimize the startup latency for one of these sandboxes, right? And the second thing we wanted to do, recognizing that we can see massive spikes in traffic and really large numbers of users coming simultaneously, we also wanted to maximize the number of concurrent sandboxes that could be run at a time. Right? So those are the two primary goals that we had. I will probably breeze through the next couple sections because you all know how compilers work. I stole some of these slides from an industry talk I was giving where I have to assume that people don't really know what a compiler is. They just assume it's magic. So Lucet C is the compiler side of Lucet. Internally, it has a whole bunch of different parts. Obviously, we have a parser, walks through the data structure of like a WebAssembly module that flows into a verifier, which is pretty crucial, right, in like being able to continue the guarantees that WebAssembly provides for us. Right? If it's not actually a valid WebAssembly module, we can't really assume anything about it at that point. Assuming all is well, this flows into a translator, which takes that WebAssembly bytecode and translates it into an internal intermediate representation of some kind. In this case, it actually ends up being crane-lift IR. Is anyone actually familiar with crane-lift at all? All right, a couple of you, cool. I'll talk about that in a little bit. Translated IR flows into the code generator, and finally, we get the artifact that comes out of it. What's interesting about this artifact is that it's machine code, of course, yes, but it also contains what I refer to as a contract that goes along with it. Because Lucet is actually an ahead-of-time compiler, because that fits our model really well, we need to be able to essentially cooperate between the compiler and the runtime, despite the fact that they're running in different places at different times. Okay. Is the fact that like in our ideal world, like because of the way our model works, we don't really want a JIT of any kind. We want an ahead-of-time compiler. So we compile it once in one centralized location. We spread that out to the thousands of servers, and then they can all run it. And the whole idea is to like make that part as fast as possible. We essentially don't really care how long it takes to compile something. Okay, so the code generator here is, like I said, it's crane-lift. So crane-lift also has a verifier in this case, but in this case it's verifying the crane-lift IR itself. Once that's verified, we run, why am I even going through this? You all know what an optimizer is, and legalizer. The whole point here is that like crane-lift is actually the thing that is doing the vast majority of the some of the like the heavy hitting work inside of this compiler. It was built by a relatively small group of people at Mozilla, along with like people from Fastly and several other places as well that are like contributing over time. But it's actually a pretty good piece of software. And so if you're interested in this kind of thing, like I would recommend checking it out. All right. So, oh yeah. Figured there was always a chance that like I would just do a terrible job, but I would still mesmerize all of you with my animations. My goal here, because LaTeX is just can't. Right. So that's kind of the overview of like the compiler itself. It's that part's not terribly interesting, to be honest. Like, you know, I spend a lot of time on it, but like that's not where the novelty in the system comes from. But so there's also like the runtime that goes along with it. It's where a lot of like the rest of the complexity and interesting decisions and trade-offs inside of Lucet live. So the runtime is critical because this is the way that this is essentially the way that we get performance out of the system, right? And especially the startup time because of how we approach the relationship between the compiler and the runtime. The artifact that Lucet produces doesn't just contain code, like I mentioned, it contains like metadata, essentially a contract that says effectively like I, the compiler, claim that this code is safe for you to run as long as you set up the environment according to this set of specifications. So runtime also consists of several components that have to work together. So we have a loader that knows how to interpret that artifact, read the contract, understand the layout, and so on. And we have, of course, yet another verifier or validator because, you know, why not have 5 of them? The validator in this case is the thing that actually interprets that contract and what's in the contract. So what is in that contract? So essentially, this is a lot of what is in there. So we're talking about like minimum required memory. And so essentially the validator needs to go through and go like, okay, am I configured to allow this much memory per instance in my system? If not, I have to reject this program. Is this compatible? Is the required virtual memory for one of these compatible with the like allocation sizes that I have set up? And we'll talk about why that's so important in a little bit. The exports and the export types, match the types I expect, import types and so on. Am I allowed to actually provide access to these functions? For the fault handling protocol, do I know the fault handling protocol? Like if not, like, you know, a signal coming from the thing will mean something very different. And finally, is the expected memory layout the way that I have laid out my instance memory? We'll also come back to this one. because this is again the way we get a lot of the performance out of the system. Is like being able to make certain assumptions. So if we take one of these, for instance, like the required virtual memory, is this compatible with my allocation sizes? Why does that matter? This may be obvious to some of you, but like in a naive setup, like let's say this is the one line of code that we're trying to compile. Like my array, I have a local array of some kind. I want to, set the 17th element of the array to 0. So in WebAssembly, that might end up looking something like this. I'm going to get the my array local variable. I'm going to push that onto the stack. I'm going to push a 0 onto the stack because that's what I want to set it to. And then I'm going to store this at offset 136. Makes sense. So depending on the size of the heap and the size of the virtual memory, we may be able to make different assumptions about what this might compile to, right? So let's say our heap in this case is just a heap. There's nothing special about it. It's just a set of memory, and that's all we know. That's all we got. So in this case, we might need to actually do quite a bit of work. If we're going to follow the WebAssembly spec like to the letter, that one store might look something like this, where first we need to essentially we need to, let's say in this case that my array is in the like RAX register. We first need to bounds check just the base of that array, right? Assuming that goes well, then we're going to look for the last byte that we are even considering setting on this thing. We have to bounds check that as well. All right, and then assuming that is okay, then finally, all the way at the bottom here, we can actually just set it to 0, right? So that's assuming that we know nothing about the heap. If we know a little bit about the heap, if we know, for instance, that there's a like 4 kilobyte guard page at the end of it, then we can make some more interesting assumptions. What would that potentially get us? So in this case, let's go back to the exact same line of code. Now, if we know that there is 4,096 bytes following the heap, we will know that, yes, we need to bounds check the base of my array, but I also know because this is a like constantly defined place inside of there that I don't like, as long as the base is within bounds, I know that I can set this, right? I know that it will not go beyond the guard page, which is our other way of bounds checking, right? And so what's even better about this is then if we have a whole bunch of these set in a row, we can actually bounds check once and then remember that information across different stores. And so finally, one of the more useful things about WebAssembly's setup is the fact that pointers are always 32 bits in WebAssembly. So if we take that 4 kilobyte guard page and we extend it to be 4 gigabytes instead, what does that end up looking like then? Well, in that case, we can actually just elide all of the bounds checks. Great. So why is that? So the whole point here is that because the guard page, because the pointer cannot possibly go beyond the end of the guard page, because there is more than 32 bits of space there. Make sense? Yeah. So essentially, like the point here is that like it's not like about bounds check elision. Like I'm sure you all know about bounds check elision. The point here is that like in order for us to be able to make that assumption that we can do bounds check elision, we have to know for certain, if we're going to maintain safety, that the runtime is actually going to set up the memory space in the way that we expect it to. So it's built into this contract. So, so it's finally time, like some sort of external stimuli comes along into the system, and we want to run the damn thing, finally. Okay, so what is involved in running something inside of Lucet? So Lucet is built entirely in Rust at this point. Rust and like a shrinking stack of assembly code at this point, which is good. But so right. So essentially, like the instance struct here is the primary thing that is associated with the actual like running of one of these instances. You can see that there's a context in there. So starting an instance involves a context switch. So we have a place to stash the current context as well as a parent context. We can swap back to it. Not terribly novel, but like that's what is involved. I've removed a whole bunch of stuff from the instance here, and I also know that I'm standing in front of it, so you can't see it anyway. But there's these are some of the more interesting things in it. Like state knows the current status of an instance. Kill state is used for things like timeouts, so we can remotely kill instances from separate threads in the system, which is one of the trickier parts that I have absolutely zero proof that it works, other than the fact that it seems to work. But like the interleavings of it explodes. Signal handler is used for handling faults, such as those UD2 instructions that I showed in the assembly there. And resumed val is down here because Lucet also can do suspend and resume semantics. alloc is interesting though. So alloc is mostly composed of this concept of a slot. And the slot is what defines the memory layout of an instance. Okay. So if we go back to the list of things that were in the contract, one of the things is the expected memory layout. And this is not just about like the size of the heap and the size of the size of the virtual memory, right? There's actually more to this in order for us to be able to get performance out of the system. So the memory layout of a Lucet instance might look something like this, right? So we have instance metadata at the top, followed by a heap, followed by a guard and stack and globals and signal stacks and so on, right? But of course, like, again, this thing was meant to be able to run like many, many, many instances all simultaneously, right? So it's not just this one, it's actually a whole bunch. And due to the way that like the request distribution comes into a system like ours, and due to the number of like different programs that are being run at any time, it may actually end up looking something like this. So we have the concept of what's called a region built into Lucet. And so these are essentially fixed size slots. So it's a contiguous area, contiguous region of virtual memory in the system with fixed size slots that one of these instances can fit into, right? And so the whole goal with this is for us to minimize the number of VMAs. VMAs are a concept inside of the Linux kernel, in case any of you don't know. The whole concept here is that like these take memory and time for the Linux kernel to process and deal with. And we want to minimize the total number of these. So if we can shrink these down to like, you know, having one or a relatively small n of them, that would be useful. So these get flipped on and off, kind of on demand, right? And again, this is a contiguous area of memory, so we're just flipping them on and off. So essentially they take up zero memory while they're off, or relatively close to zero memory while they're off, and then they get flipped on, become actual physical memory, and then get flipped back off again. And so we here, which I will skip over because I realize I'm getting kind of systemsy for this group. But essentially, yeah, so this is one of the more useful parts. This is actually the part that gets us the majority of the like startup performance. And I will explain why at this point. So, because of the way that we can assume, you know, at compile time what exactly this is going to look like, right? That means that we can basically set RA, like when we're trying to start one of these up, we just set RAX to always be pointed at the beginning of the heap, right? So we have a fixed point within there, and then we can make assumptions about where everything else is based on that. So essentially starting up one of the Lucet instances comes down to save registers, choose a slot in the region, set registers, and jump. So the novelty about that is that pessimistically it takes around 50 microseconds for us to do that. Interesting about Lucet, that this thing that is completely different about it, that makes it useful for our use case, right? Because that is like a kind of ludicrous number when you look at like what other sandboxes do at the moment.
Sorry, I don't get it. So
Yeah.
what exactly is a slot?
Okay, so when we first allocate an enormous slice of virtual memory,
Okay.
going with it, right? And we say like, okay, here is how we're going to lay out the instance within this, so it will take up a very specific set, like a very specific size, right? And so then we just tile those across it.
So what does it mean to choose a slot? You literally translate the
Literally, it means to find one of the open ones,
Yeah.
and then do some see how to put it. Essentially flip the slot on. It's essentially like making sure that slot actually has physical memory backing it.
This I understand, but
Yeah.
if you choose a different slot the next time,
Right.
either you have to change the page tables,
Yeah.
or you have to copy data. What exactly do you do?
So you do end up having to change, well, so you kind of have to change the page tables. You actually just have to, like, in the most trivial case of this, it actually just comes down to an mprotect call.
Okay, yeah.
Right.
All this is based on MPTs.
Well, what's that? Sorry?
Oh, memory protect. Yeah, okay.
Yeah,
okay,
So like, that's the most trivial case.
Okay.
We do some different things, like we have like an actual kernel module that will
Yeah.
go do this lazily for us.
Yeah.
But yeah, essentially the point is that like as long as your program just is entirely based on what the value of RAX is and everything else is like an offset from that, like we can just move it around in all these different
But
slots.
then there's also a lazy cost because of the cache missing. Cache code cache missing.
That is
How-
true.
How do you deal with that one?
How do we deal with that one? We don't, we just eat the cost of that. That's, yeah. I haven't found a good way around that one yet.
Yeah.
Yeah. Okay. So again, inside of Lucet, there's a whole bunch of other stuff that's in here. You know, the memory manager is actually what I was just mentioning. Like, there's a whole bunch of different ways that we can manage those regional slots. Like, Linux actually has some more interesting things built into it at this point, like user fault FD, letting you handle faults that occur in user space without having to hop back to the kernel and assume its semantics for it. You can actually do some interesting lazy memory management with that. We need to handle things like timeouts, instruction counting, debugging. Yeah. Right. So there are a bunch of caveats to this. There's only a certain set of like safety and security guarantees that this entire model gives, right? So obviously, if we're going to run this in a real-world system, it looks more like that. And we have been talking solely about this. There's a whole bunch of other like protection that has to go in place below that in order to like keep the infrastructure safe from malicious users, potentially. Part of that is like just defense in depth, and part of it is just because like that's the right thing to do. It's like, you know, best practice at this point. So that's kind of my overview of Lucet. Kind of weird and disjointed, but I'm going to stand behind it. There are some interesting problems that we have though. So one of the biggest places that we are finding bugs and finding issues in our system, and I think that a lot of other people are also finding issues in their system when they have a sandboxing system, is how you ensure safety across the host-guest boundary. This is like one of the like gnarlier problems for us that like we just don't have a great way to solve, that I'm kind of looking to all of you to hopefully solve at some point so I can just adopt it. And so in our case, like a lot of it is just plain old bugs, right? Like as soon as you start passing values back to the host, I have basically zero guarantees about what happens out in the host with those values. It gets like somewhat more complicated because of the fact that inside of Lucet you can be running, provide a callback, like call out to the host, providing a callback back into the guest, and do that repeatedly, going back and forth. During that time, you may be passing references in and out of the sandbox. Those references could be overlapping. So there's all sorts of like gnarly problems that come out of that, which we're just constantly fixing bugs with.
Maybe one in the previous. So where exactly? Where there are bugs in like Linux system code?
No.
Or even just in your own code?
So I'm talking about in our own code, because the API that is provided to the sandbox is actually like fairly large, right? It needs to do fairly complex things, right? So that's actually just like within a single process. One of the other ones that like has been a surprising source of pain for me and my team has been how we enforce fairness across guests. Right now, most resource limitations are enforced from the host, and some things are built in. Like, you know, obviously maximum memory was one of the things that's like built in that contract. But we have problems with, say, like import, like syscall policy, right? So I have zero guarantees about the number of times or the order in which or anything that a guest will attempt to call various syscalls. We can impose that policy, but it's going to be kind of piecemeal depending on what we happen to decide at that point. Yeah.
So with fairness, you mean that you would like the guests not to starve each other?
Yes. exactly.
On the various resources that the system offers.
Yeah, yeah.
This is called other form of resources that are
That's a good one. Well, so I think the vast majority of them will end up being like things that involve syscalls, but then there's also just, the obvious things like, what if I have an infinite loop? Eventually that has to be picked up by a timeout, but you've taken probably a significant slice of time before that. We can do instruction counting for that and build that in. That tends to get expensive. Maybe there's a different way to do it. But the other point of these is that like they all tend to end up being like kind of whack-a-mole style. Like the only way that I know that they're a problem is because someone abuses them, and so then we end up just what that ends up implying to me is that there is constantly holes in the system, and I don't have a like holistic way to actually like solve them.
So why do something really coarse-grained work here, where you say, okay, you can do whatever you want. If you really start hammering my system, I'm going to kill you.
That is how it works.
Okay.
Right.
So,
The point is that like in the time between you started hammering my system and I decided to kill you, you've taken up way more resources than like anybody else has, right? And like that may have starved other customers at least for a short period of time.
Yeah.
And again, I think even more importantly is just the fact that I know, like in the back of my head, I know that there are holes, right? And I don't have a like provable way to actually solve the problem. Right, it implies gaps. And I know there's at least one person talking about this today, but how can we provably prevent transient execution attacks? So let me caveat this one by stealing a saying from one of the primary people I worked on Lucet with is a guy named John Fudd. He's our principal security architect at Fastly. His statement is that transient execution attacks are the ultimate well actually device, because the reason for that is essentially that like there are so many unknowns, right? Like, well, I don't know, is that secure? Have you considered Spectre? Fucking kill me. Anyway, it's a whole thing. That said, we do have like a pretty damn thorough plan for how to deal with transient execution attacks in the system that essentially ends up amounting to being incredibly pessimistic and having like incredible defense in depth. I was mentioning this earlier. There's a bunch of steps that are necessary to pull off a transient execution attack, and our intent is to attempt to break all of those links in the chain, right? Rather than just trying to prevent transient execution or just prevent timers or just do this thing. If we're going to not use the Linux's built-in ways of dealing with this problem, we're going to attempt to break all of the different chains. But ultimately, again, that ends up just being whack-a-mole. Right? If we have a provable way to do this, that would be incredibly valuable. Okay, one last thought before I stop running my mouth. So Fastly has a certain set of use cases for all of this, and obviously they're pretty important to me personally. But I think the industry context for what we're talking about here is actually quite a bit larger than that. Companies and users are clearly pushing to a more and more distributed way of doing computation. And in fact, as a side note, this project actually started with me wanting to create a massive peer-to-peer coordination-free data system, so users could build stateful, globally distributed applications on top of it. But I realized I was going to need a safe and fast runtime for that, and now it's 3 years later. God. So the way that people are trying to build that right now with massive container and virtualization stacks is just, it's not going to work, right? We have incredibly slow startup times. We have absolutely egregious resource usage with these things. We need to find ways to make that a safe, efficient, and cost-effective way to build applications. Essentially, we need a way to that is safe, efficient, and cost-effective to run applications on anything from big metal servers like I use down to embedded medical devices, for instance. Because right now, those systems are either centralized and thus unreliable because you're requiring network connectivity in order to actually get things done, or they're slow and bogged down by these layers of abstraction that we're imposing upon them, these layers of security abstraction that's being imposed on them, or which makes them unusable, or they're neither and thus probably unsafe, right? So that's why, to me, I think that's why I think these types of problems are actually incredibly valuable for us to solve, and why I think the type of work being done by many of you here is actually incredibly worthwhile. So thank you for that, and I'm happy to take questions. So part of it is about security, but a lot of it is actually just about like the way that the compiler decided to compile the program. So it's making certain assumptions about where things are located in memory. So if I need access to like the tables, like WebAssembly tables, or if I need access to the stack or to globals or anything like that, I know ahead of time, I have imposed ahead of time where exactly they are going to be located relative to the start of the instance. And so it's really more about that, having like being able to avoid abstraction layers in between there.
So in these individual, I don't know, instances, do you also inject any code from the outside, like libraries?
Do we inject any code from the outside, like libraries? What's the context of that? I don't totally get it.
So for example, if you look at something like libc, okay, where does that?
Yeah. So libc is something that may be compiled into the sandbox. It may be compiled into the program that we load in the sandbox.
Yeah.
We provide effectively like a POSIX-like system interface.
Yeah.
It's called WASI, for the sandbox. So basically anything that like, which is like a relatively low-level interface for the entire program, right? So like you can essentially you can bring your own libc if you would like to. That's the point. But the libc exists inside of the sandbox.
Inside of the sandbox,
Yeah.
and it's also compiled via WASM basically. So it's
Yeah, absolutely.
I see.
Yeah.
Okay.
Which has its ups and downs.
And
I think maybe in that figure, like the code segment was missing.
yeah, this is
That's
exactly what.
maybe-
Also libc
Oh,
state.
in the memory layout?
Yeah,
That's because it's not in there.
right.
Right.
Oh, that's a shared across the instance.
It's shared across all the
No,
instances, right?
No, actually, I was more worried about libc state. Libc has state.
I'll let him do it, but
I don't have a great answer for that.
Okay. And what happens if your application wants to share memory across users?
That's something that we don't support at the moment, but is theoretically feasible inside of like the WebAssembly spec, right? Like you could actually have multiple different memories. You could share memory via like, well, the trivial way is to share memory via copying, right? But that's actually something that we're working on specifically with the WebAssembly interface types, trying to figure out a good way to do that. So I don't have an answer yet, but hopefully we'll see.
I have a question about the kind of attacks are you worried about?
Yeah.
The host guest owner.
Yeah.
Like is it, I don't know. I mean, you said you use Rust, I guess, for the host. So I guess you are not vulnerable to most memory safety kind of attacks?
That's true. It's not so much memory safety that we're worried about, although like there's, just due to the way that we like have to interact with the sandbox, there are a bunch of like bits of unsafe code in there that, you know, are thoroughly tested, but again, I have no proof. Most of what we're worried about at that layer is more like protocol violations. So for instance, so effectively what happens is this, like we're providing a capability-based API to the sandbox, right? That one of those capabilities may be, okay, I have an HTTP request that came into the system. I want to give you the capability to get that request from the host, right? What happens if I try to get another request from the host after that? Or what happens if I try to send 2 responses to a single request? Or what happens if I try to send 10,000 requests out like to different servers, right? A lot of it is about abuse, and some of it is about like essentially bugs that we weren't that we had not considered, right? Things that we did not think a guest would even consider doing.
And they're pretty much at the logical level.
Logical level, yeah, for the vast majority of it, yeah.
Sorry, I have 2 more very quick
Okay.
questions.
Yeah.
So just one is a clarification.
Yeah.
So did I get it right that because of this these gaps that you have in the layout, you really don't need any pointer checks, bounce checks?
I would not say that that is true. We need certain pointer checks, we need certain bounce checks, especially in things like table lookups.
Oh, sure.
Yeah.
That's a very good. But in general, for memory access, you don't really need the bounce checks.
That is almost entirely true, yes.
Okay. And then, what kind of language level support would actually help with this kind of compilation? I mean, one thing is that somehow in your language now you need to talk of these user to instance mapping, right? So I'm thinking of, suppose I wanted to take a language like Python
Yeah.
or Rust or whatever, wherever I'm writing my application, what would I need or what annotations would I need to be able to leverage this kind of backend?
To leverage what kind of, sorry, I didn't follow that.
Here what you're doing is you're separating instances, you're mapping users to instances, right?
Yeah.
It's not the case that languages have a natural notion of user per se, right? That's something that's built into the application somehow.
Yeah. So the way that we are set up, it kind of more or less emulates a process.
No, that I understand.
Okay.
Yeah, but sorry, I'm going back to my earlier question where you want to write a single application that probably has shared state across users.
Oh, I see. So I guess in principle, what we would assume then is that there is like, perhaps we need to be able to provide like an IPC interface of some kind.
Oh, I see.
That's like a virtual IPC
Yeah,
interface.
sure.
Or something.
Okay.
But yeah, like I don't know, that one I haven't really thought all that much about yet, to be honest. Yeah.
Another question regarding this host guest boundaries and security there. Do you imagine that at one point you'll be able to give guarantees for your hosts that your guests that they are protected from the host somehow? So for instance,
Right.
if I have my highly secure encryption key and I want to put that into my instance,
Sure.
but I mean, yeah, I trust you to run my program, but would prefer not to let you know my encryption key.
Yeah, for us, that's probably not ever going to be a thing that we care about all that much, but I know that there are others that do. I know some folks at Red Hat are working on this specific problem as well. But yeah, for us, like, there's a tremendous amount of trust that's actually involved in this entire thing to start with. Like, people have to give us their TLS keys, for instance, in order to use this. So like, yeah.
I have to give you my keys anyway. So.
Exactly. Like, I have the keys to your car at this point.
Can we, last one, if it's quick?
I don't know.
Oh.
So can you elaborate a bit more on the transit execution attacks? So what kind of attacks have you sort of, what's your attack?
I mean, I'm mostly concerned about, what are the attacks I'm concerned about? I don't know, basically all of them is essentially what it comes down to, because like, given the fact that we're like allowing users to execute completely arbitrary code, and we're executing a lot of these things inside of a single process, like I'm concerned about them attacking other guests, I'm concerned about them attacking like the host itself. We provide like other kinds of protection for things like TLS keys, like those don't live in the same process, but there is undoubtedly going to be like valuable things within the process, right? Because like a lot of the point of this system is that we don't want to impose process boundaries wherever we can, because it implies IPC, it implies like kernel level context switches, which are expensive. Have inside of that single process, and still get like transient execution protection. Like that's what we want to do. That's my answer. As short as I can be.
All right.
Awesome.
Thanks so much again.